Okay, I guess it's about time to start. Okay, are there any questions before we get started? So I like to go on and talk about circuit theory. We visited circuit theory again because circuit theory is very important. You have KCL and KVL. Okay, and then you have all these laws. And the reason why we want to visit it again is that you can think of circuit theory as coming from Maxwell's equations, but they're a lot more useful compared to Maxwell's equations because they're very simple. They're very simple to solve and also very easy to model things with circuit theory. And hence, the whole microchip industry is actually fueled by circuit theory IC designers. This is integrated circuit designers. Okay. And it would be good to know some electromagnetic theory so that when you work with circuit theory, you know what you are doing and when the regime of circuit theory is valid. Okay. So we can easily, for instance, apply Kirchhoff voltage law. Kirchhoff voltage law to a circuit where this is a battery before. Okay, so this is like having a battery. And you can show that you can write KVL around this loop, which I hope all of you know how to write. But then one thing that is new to you perhaps is the fact that if you have a battery, you can think of a battery as being a negative resistor. Okay, so the concept of a negative resistor is important. Because if you think about it, what happens inside the battery is some chemical processes. The chemical processes is such that it moves the, if you don't mind me using positive charges, because actually electrons have been moved around, but actually it moves the positive charges from this end to the other end of the battery. And so if you think of it that way, the electric field is actually pointing in this direction from positive charges to negative charges, and they have been held in place by chemistry. So when the electron or the current is going around, actually not electron, we always think of currents as being due to some positive charges, only very late in history that we know that it was not positive charges that carry currents, it was electron. So electrons are going in this way, positive charges are going this way. And when the positive charges are going against the tide of the electric field here, you actually have to do negative work. And in that case, negative work is equivalent to generating power. So we know from Poynting's theorem that the current and the electric field generates a kind of energy in this manner. And if J equals sigma E, then this energy, this is power dissipation, for instance. power dissipation is actually equal to sigma E dot E, okay, or is equal to sigma E squared. And you can write this both in the frequency domain as well as the time domain. And if this is negative, it just means that instead of power dissipated, power is generated. So you can think of a battery band, a negative resistance in this new twist of things. And in fact, there was a person by the name of Isaki, where he used negative resistors to model transistors. And he was awarded the Nobel Prize for his work. So Nobel Prize does not have to be associated with very complicated concepts. If the concept is simple and easily acceptable, then you have a widespread acceptance of the concept. So let's think about Kirchhoff voltage law applied to a circuit like this, where you have resistors, inductors, as well as capacitors. Okay, we can apply Kirchhoff voltage law to this loop, and Kirchhoff voltage law essentially follow from this equation, which is Faraday's law. And if the right-hand side is 0, which is the low frequency limit, we have curl of E being equal to 0, and then you can write this equation as using Stokes' theorem is equal to minus d dt of mu h dot ds. Okay, where S is the surface that's enclosing the loop, or the loop forms a surface. You can write this Faraday's law in this manner. This is usually called the flux linkage. And for most of the time, you can assume that this flux linkage is 0. Okay, if partial t is 0, or if things are very slowly varying, and then you have this Kirchhoff voltage law that can be derived. So you derive Kirchhoff voltage law by integrating this in the loop, and you will get E dot dl is equal to 0, okay, around the contour C. Okay, is there any question about Kirchhoff voltage law? This is KVL. Okay, this is essentially KVL. Okay, so if you were to do that, then you will integrate the electric field in the loop around this structure. And you assume that B is equal to 0 in this loop, so that partial t of B is equal to 0 in this loop, so that this term can be thrown out, or this term can be ignored, and this term can be thrown out. And if you do that, then you essentially have the rule that curl of E equal to 0, and then you will have E dot dl in a closed loop C, okay, is equal to 0, and from which you can find KVL. So we can see that there will be a voltage drop. Voltage drop, in the beginning, it was a voltage source. The electric field goes in the opposite direction to the movement of the current. But then we will have VBC here, and then we have VCD here. The voltage drop is VBC, and then there will be a voltage drop here, which is VCD, and then there will be a voltage drop VDC. Okay, and only over the last bit, the voltage drop is negative. So we can show that V0 plus VCB plus VDC plus this should be DA, okay, plus VDA, not VDA, sorry, VAD must be 0. And I'm defining VCB to be the negative of VBC. And then I'm defining VDC to be the negative of VCD. And then VAD to be the negative of VDA. And I'm defining it such that if I were to integrate E dot dl from a point A to B, for instance, from the point B to C, okay, from the point B to C, and then it would be VC minus VB, and then it would be VCB. Okay, so if you integrate this around the loop, the first integration will give you VCB, the second integration give you VDC, the second integration, the last integration will give you this. But I'm defining the voltage drop to be positive in this manner. And if you go and work out things correctly, you will have this to be your Kirchhoff voltage law. Okay, so this is KBL. And then in deriving that equation, you have assumed that E is equal to minus grad phi. Okay, so this is quite easy. So we actually can establish KVL very readily. And are there any questions regarding this? These are undergraduate material for many of us. Yes?
What about the induction effect?
Oh, the induction effect is going to be discussed in the next slide. Okay, I'm going to discuss the induction. I'm going to integrate on a loop that does not go through the inductor. Okay, so this loop encloses no B field. The B field is inside is equal to 0. So the induction effect is going to be 0 on the right-hand side, and I can apply KVL. But then I have to relate VCD to the induction integration over here. So let me look at this induction effect more carefully. Okay, if I were to look at this more carefully, that's a good question. So what I have is that if I were to integrate from VCD, which is what I did before, okay, I just integrate from VC to VD. And how is that related to the flux linkage in this problem? So I'm going to define a new integral. And that integral I call C prime. Okay, C prime is going to go like this, as you can see here, and then go from here to here. And then E dot dl. And this is going to Hello, can you hear me?
I can hear you, but I see a green screen.
Yeah, you definitely disconnected for a little and the screen is green at the moment.
Apparently my power charger is not working. Let me put this other power charger on. Okay, let me see if it comes back. Okay, let me see if I can connect my computer screen again. Get these electronic things to work well. I don't know why it suddenly stops working. Even though the light say it was working, but suddenly it went dead. Okay. Can you see me or can you see the screen? Hello?
I can see
Yeah.
you.
We can see
Can you see the
Professor.
screen?
No, I
No?
can't.
You can. Okay, let me do screen sharing again. Okay, can you see the screen now?
Last screen is here.
Okay, can you see the screen now?
Yes.
Okay, good. So it comes back on again. It was disconnected for a little while. So we can apply Faraday's law to this loop. Okay, we apply Faraday's law to this loop. And essentially what I want to do is to connect the VCD in the previous picture to the flux linkage of this inductor. So if I do that, then I can show that this integration is related to VCD. And first, let me assume that I have a PEC wire. Okay, this thing is made out of PEC wire. Let me place my thing so that it's easier for me to write. Okay, so if I assume that I have a PEC wire, then E is equal to 0 inside the wire. And when I do this integration around the PEC wire, around the loop C prime, the only integration that is not going to be 0 is this last bit of integration over here. So this would be E dot EL from D to C. Okay, let me put C here and put D here. So this is going to be D to C, and the flux linkage is not going to be 0. The right-hand side of Faraday's law is not going to be 0. And if I remember the right-hand side, it can be written as B dot ds, okay, over the cross-sectional area A of this loop, okay? So I'm going to pick up only the last bit of the integral and assume that in this gap, in the gap where I'm doing the integration, okay, I can define a voltage, and this is equal to VC minus VD. Okay, that last bit of integration that I pick up is going to be VC minus VD. And you can go to your potential theory again, where you can assume that the electric field is the negative of the gradient of psi. And if you go through the analysis, you find that this is true, okay? And if this is true, then I'm going to assume that partial A. So when I write this down, I'm also ignoring this term. Okay, I'm ignoring this term and saying that this term is 0 here. Okay, there's no magnetic field there. So this is approximately equal to 0. I'm only pick up the electric potential term. So if I do that, then this integration that I have on the left-hand side is just equal to VC minus VD is equal to minus d dt of B dot ds, okay, over the cross-sectional area A, and this is VCD. So I am able to relate VCD to the flux linkage, and I can write this as minus d dt of Li. Okay, and this is my flux linkage. Okay, then if I rewrite the fact that I'm actually working with V in the previous picture, I'm working with VDC in the previous slide. So essentially I have VDC equals to d dt of Li. Okay, and then this becomes L d dt of I, where the flux linkage, the inductor is defined to be the flux linkage per unit current. Okay, if I plug that in, I will have B dot ds over A divided by I. Okay, if I use this equation, the L, the constant L, is essentially given by this formula over here, where I assume that the magnetic B, the magnetic field B, is proportional to the current. Okay, the magnetic field PB is somewhat proportional to the current. And because it's proportional to the current, I can define a constant called the inductor in this manner, which is the flux linkage divided by the current. And I have this IV relationship of an inductor. Okay, this is what we often see in an inductor. And so if we put that in, then we have another piece that we need to change here, which is that VDC can be replaced by this number over here. And let's look at the capacitor. What happens to the capacitor term? Well, if I were to look at the capacitor term, it's going to be something like this. Okay, let me put a new slide. And what I'm going to have then is that in the capacitor, I know that Q equal to CV. That's the definition of a capacitor from our undergraduate days. And then let me see what symbol I use. So it would be something like VDA. Okay. And if the capacitor is having a voltage of VDA across it, okay, then I can use this formula and I can say that I is dq dt. The rate of change of Q gives me I on the outside. And then I essentially have I is C dV dt, okay, from this equation. And this gives me the formula for the definition of the capacitor as well as the IV relationship for capacitor. Okay, previously that was the IV relationship for an inductor. Okay, what we have here is the IV relationship for inductor, where for the case of the inductor is V is equal to L di dt. This is the IV relation for an inductor. Okay, so we have all this IV relationship, and then you can go about deriving the IV relationship for a resistor. That I wouldn't do because you probably have seen that done many times in your undergraduate studies. Okay, so the IV relationship for a resistor is quite easy. V equals to IR. For a resistor. Unless you want me to do that, I wouldn't do that. Okay, is that okay? I just skip that IV relationship. The IV relationship for a capacitor, IV relationship for an inductor, and an IV relationship for a resistor. And then you have almost all the components that you need for using circuit theory. Okay, any questions so far? If not, then I would just want to emphasize one point, which is that even though we say that circuit theory is an approximation of Maxwell's equations, it's not too bad an approximation in this sense, okay? It's not too bad an approximation in this sense because Maxwell's equation, we started out with Faraday's law. Okay, and then we have Ampere's law. And we say that when omega tends to 0, okay, we have Faraday's law becoming like this, and then Ampere's law becoming like this. Okay. However, we actually have dB dt not equal to 0 for an inductor. And then we have dB dt not equal to 0 for a capacitor. So in circuit theory, we do not drop these two terms all the time. We only drop these two terms when they are unimportant, like outside the capacitor and outside an inductor. So we keep these two terms inside an inductor and a capacitor. So not all of not all of Maxwell's equations is lost in circuit theory. These two terms are very important, as you have seen before, for capturing wave phenomenon. And because of the inclusion of these two terms, we can actually capture wave phenomenon with circuit theory. And a very good example is this of a transmission line. We notice that we can use circuit theory to describe a transmission line, as long as we don't throw out the capacitors, okay? And this eventually becomes a transmission line. And we have the Telegrapher's equation. And from the Telegrapher's equation, we see wave phenomenon, where we saw that, well, we have from the Telegrapher's equation is P is equal to minus L di dt. L, I is equal to C dB dt. Okay, from this Telegrapher's equation, we get wave. Okay, so now all is lost in circuit theory in the sense that we can emphasize this term with an inductor, and this term we can emphasize with the capacitor. And we get back wave phenomenon, okay? There's one thing I want you to understand. And inductors are very important in circuits, so are capacitors. In circuits, for instance, in a microchip, they often make spiral inductors. Spiral inductors that look something like this, that it's very hard to make inductor on a microchip board. So they get wires like this, and then you will have a connector, okay? Say, so this essentially is what a spiral inductor is. And so when current passes through this structure, it generates a very strong magnetic field B. Okay, because it generates very strong magnetic field B, it stores magnetic field energy and it behaves like an inductor. Okay, so I like to also emphasize that in the microchip, it generally looks something like this. You have transistors at the bottom of a chip. Okay, these are transistors with NP junction, NPN, or PNP junction that you might have learned in some of the courses before. And then the three terminals, you need input, output, a drain, and a source, and a gate kind of circuit description. And then they need to be connected to the outside world. Is somebody talking in the background? Because if you can mute your microphone, that would be good for me. Anybody? Brandon Roque, you have not muted your microphone. Okay, good. Brandon Roque, you have muted the microphone. Thank you. Okay, so So what happens is that this is what happens in the computer chip. All the signals are connected to the transistor, and there are now, what is the last time I heard, 7 or 8 billion transistors on the cell phone or on a microchip. Okay, and then they're all connected to the outside world, and then finally they're connected to these lines, which look like XY lines. They're like X and Y in the direction. They make a multi-layers, and by connecting them properly, engineering them properly, you can get a ball grid array. This is a ball grid array, which actually is on the top of this package. Okay, you can get these transistors to talk to the outside world through this package. So there is a lot of electromagnetic engineering, if you want to understand that, and it's actually amazing that we can do this kind of things nowadays. So the thing is that all these things are very small compared to wavelengths. Okay, L is much less than lambda, and a computer circuit switching speed of a microchip has not gone beyond 3 gigahertz very much. So you have wavelengths that are about 10 centimeters. No, am I right? Yeah, about 10 centimeters yeah, I guess so. Let me see. Yeah, wavelengths is about 10 centimeters. So all these structures are much smaller than the wavelengths. Okay. And hence you can use circuit theory to describe whatever you have in there. And there's a very famous program called the SPICE program, which stands for Simulation Program with Integrated Circuit Emphasis. This was developed at the University of Berkeley, UC Berkeley. Okay, and it's very useful in the microchip industry. But we are going beyond circuit theory now. You have learned about things like Smith charts and so on. And SPICE program that you have seen recently actually try to incorporate transmission line theory as well. Transmission line theory as well. Okay, you actually get SPICE program called the RF SPICE. Okay, and you can actually incorporate transmission line theory into your circuit theory. Transmission line theory is important because of modeling retardation effect. This is very important for retardation effect. Okay, and retardation effect is very important because circuit theory alone says that everything happens instantaneously. So if you think about Laplace's equation, it looks something like this. Okay, you can think of Laplace's equation as being a special case of Helmholtz equation. Okay, we have learned about Helmholtz equation. This is Laplace. And one way to think about it is that when you let C goes to infinity, you essentially get back Laplace's equation. Okay, you get back Laplace's equation if C goes to infinity, which means that if you're solving things with circuit theory where you only solve Laplace's equation, everything happens instantaneously and there's no retardation effect. That's not true. The physics of it says that Maxwell's equations will be solved, but since we're solving Maxwell's equations approximately using Laplace's equation, everything is instantaneous. So if you excite some part of the chip, the other part is felt instantaneously. And in order to account for the retardation effect that is called a clock skew in this thing, okay, because if you start switching one part of the chip at 3 gigahertz, the other part of the microchip would not feel it instantaneously. So this is giving rise to what is known as clock skew in the IC design area. This is IC design area. And in order to model for the retardation effect, you put in transmission line theory to account for the clock skew. Okay. Are there any questions regarding circuit theory before we move on? I'd like to end circuit theory here, and circuit theory ending with a tinge of transmission line theory. So whatever you have learned is actually quite useful in the real world, as you can see, in the design of microchip, where we can put 6 billion transistors or more on the microchip. And then these things are switching at 3 gigahertz. Circuit theory can be used because the cell phone is very small compared to the wavelength. And microchip is even smaller compared to the wavelength. So circuit theory prevails, but it still has to be important that retardation effects have to be accounted for to avoid things like clock skew. Okay. And any questions regarding this before we move on?
I just had a quick question.
Yes.
Sir, about the telegrapher's equations. So did the telegrapher's equations come from the kind of the derivation, the VI relationships of circuit theory, or more of the other way around?
I would say historically, KVL and KCL precede the development of Maxwell's theory. Okay, so people knew about this relationship way before Maxwell's equations came about. People know about IV relationship of capacitors and inductors and resistors way before Maxwell's equations. And people even know that you can use transmission line or a telegrapher's line to send signals where you can have a wave propagating on it. But it wasn't fully understood because like when a signal gets distorted on the transmission line, they do not know why. Okay, because these are all approximate theory. So when James Clerk Maxwell came about, he added this term. Okay, added this term. You can see that this term is actually very similar to this term. Okay, current on the left-hand side, and then displacement current on the right-hand side. So it is no small wonder that James Clerk Maxwell feels that you should have this term in Ampere's law. Otherwise, Maxwell's equations will not be complete. So I would say circuit theory precedes Maxwell's equations. Okay, does that answer your question?
Yes, Professor, thank you. Okay,
good. So if you don't have any more questions, I'd like to talk about radiation. Radiation by first studying the Herzin Dipole. Okay. And Herzin Dipole was first studied in 1888. And if you compare 1865, this is Maxwell's equation. Okay, this is Hertz experiment. And there's some like 23 years between them. So looks like a long, long time before somebody understood Maxwell's equations and then tried to do something in the laboratory to prove that Maxwell's equations are correct. That is almost like too long for us. Things are progressing so fast by leaps and bounds in the modern world. 23 years sounds like a long, long time. But maybe at that time it wasn't too long because they do not have ways of communication like what we have in the present world. Okay. And for your information, Maxwell was in England, or maybe Scotland to be more precise, and Hertz was in Germany. So people were talking across the borders. And I guess scientific research knew no boundaries then. Okay, people were talking to different parts of the world then. And of course, a very important personality in all this game is Oliver Heaviside, as I told you before. Okay, Oliver Heaviside. He was a recluse, eccentric recluse. I think that's the right word. Somebody who does not like to socialize with anybody. And when Hertz came from Germany to visit England, Oliver refused to see him, or maybe refused to see him, but didn't want to see him for some reason. I do not know the reason. But Oliver was a loner, and he liked to ride bicycles. If you like to read about his life history. So Hertz got very famous because of his experiments. So if you go to the computer store, you always learn about clock rate, right? You go to the computer and say, what is the clock rate of my microprocessors now? Well, it's 3 gigahertz. It's usually what they tell you. And clock rates has not gone up in the computer industry for decades now. I think even when I was a young man, it was 3 gigahertz, but even up to these days, it's still at 3 gigahertz. Okay, there's actually a very good reason for that. Does anybody know the reason why clock rates of computer chip has not gone up? Does anybody know? It hasn't gone up since I was a young man. Okay, it remains there. The reason is very simple. Maybe you have enough knowledge to understand that is what we call the I²R loss, okay, in a computer chip. And you can understand this loss quite easily by using a very simple model. And that you have a CMOS transistor, which approximately can be thought of as a capacitor, because it has an insulating layer between the gate, okay, and the substrate of the CMOS. And you have to drive this transistor with the voltage source. And this voltage source has to go through wires. Wires are not perfect, so they have resistive loss, okay? So you can model a transistor being driven by a voltage source by this model. So you can see that when the clock rate goes up, the current goes up. Okay, I is proportional to frequency. And for circuit theory, you can see that right away. And if you have losses in the wire, I²R loss is proportional to omega squared. Okay, so the losses that we have in a computer chip increases quadratically with frequency. And that is too much, and the chip will get too hot. And that's why we kept it at 3 gigahertz for so many decades now, ever since I was a young man. Okay, and you can easily solve this circuit. You can see that I is approximately equal to J omega CV. Okay, C is the capacitor that you have there. The higher the frequency, the larger the current. The larger the current, the higher the I²R loss. Okay. Any question regarding this simple-minded way to explain why the computer clock rate has not gone up for decades? Okay. So another thing is that I like to talk about radiation, and I think at one time I asked you to calculate AM 920. It's a local AM station that we have in Lafayette, and it operates as a frequency of 920 kilohertz. I think somebody went and calculate the wavelength. Wavelength is on the order of meters or hundreds of meters. I don't know. Okay.
300 meters.
How many meters is that now?
300 meters.
300 meters?
Yes.
Did you say 300 meters? I'm sorry.
Yes, I calculated that it was 300 meters.
Okay, very good. So I just want you to look at this picture. So if this is the antenna tower for an AM 920 station, then the size of the tower is much, much smaller than the wavelength. Okay. So you can see that this kind of approximation can be used for a antenna tower for an AM station. And of course, when you go to FM station, they are on the order of megahertz. So this approximation may not hold true anymore. But I like to model a simple dipole. this simple dipole is called a Herzin dipole. Okay, this is called a Herzin dipole, named after Hertz. Okay, and so you can actually model the radiation of a tower station by an antenna tower here, and then another antenna tower here. They're still much smaller than the wavelength, okay? And then you have a ground, and the effective permittivity of a conductive medium, does anybody remember what that is now? Is something like epsilon complex is epsilon minus j sigma over omega, right? Remember that I can model the ground with an effective permittivity or complex permittivity. So if you're operating at a very low frequency, if omega is very low, then the Earth, the good Earth, is essentially something like this, and then it's a good conductor. So for an approximate model, you can think of the Earth as a PEC. Okay, of course it's not a PEC, but you can make an approximation saying that it's very much like the PEC at that kind of frequency like AM 920. Okay, as we said before, when the frequency is low, the conductivity becomes high, or at least the conduction current term dominates, and whatever you have can be modeled as a PEC. Okay, and so I have this Hudson dipole on the left, and I like to study it in greater detail. And this was actually first made by Hertz, and explain to you why he made it that way. Okay, so imagine that you have two pieces of wire. You tried very hard and worked very hard to drive current into this wire. No current would flow because, say, if you were to drive this with a voltage source that looks like this, okay? And so this is very much like what you have learned in your transmission line theory, that you have an open circuit here, and I that you have is very, very small. Okay, so how can I increase I? Well, I can increase I by putting a capacitor at the end here. Okay, if I put a C that's non-zero, and now if I drive the current into it, then the current would not be zero. So Hertz was very clever, so he hooked two spheres. Okay, these two spheres have electric field that goes like that. Okay, the E field. And what you have then is that you have a capacitor between the two spheres. So his circuit model for the dipole is more like this, and the current that flows, the current that he has flowing in his metal wire is not zero. And that is his picture. This is from some historical picture that I got from the Wikipedia. Okay, so there's a current I that flow here, and that current I is something like J omega Q. Okay, the Q is the charge on the sphere. Okay, the current is J omega Q, and so that was what he did. Very clever. And then he actually went and drove his antenna using a transformer. And he has a DC thing, a DC battery, and he switched this thing on and off, and that gets the transformer to be time varying, generating a voltage source on this side, and that voltage source is used to drive the Herzin dipole. The Herzin dipole can be modeled as two capacitance bank at the two ends, and then he picked the field out using a loop antenna. And his loop antenna looks something like this. We'll study a little bit about loop antennas later on, and he observed sparking gap at the gap of this receiving antenna, and at the time his antenna looked something like this. Really crude, but very, very important. Okay, so I like to start the Herzin dipole A dipole field actually looks something like this on the right-hand side. You have a positive charge, you have a negative charge. We have studied this problem a few times over. The electric field looks something like this, okay? And if you are close to this dipole, the detail of the electric field looks something like this. Now, if you assume that this dipole is very, very small, and your observation point is quite far away, so you're observing this dipole out here, okay? Then the field is going to look something like this. So you can't tell the difference between whether this is a point dipole or a small dipole. So if a dipole is small enough, it can be approximated by a point dipole, okay? So once we have this point dipole, we can approximate with a current source that is point-like. And we're going to study this radiation of this current source, okay? So we are going to have a current that is, say, pointing in the z direction with the current moment, and then it is going to be a point source looking something like this. And I will give you the rationale for this model. It would be delta x, delta y, delta z. I think you have come across this mathematical symbol before, okay? And of course, the sanity check that you have to do is to check the dimension of this equation. Left-hand side is in terms of amperes per meter, or per meter squared, that's current density. This ampere meter, and then this 1 over meter times 1 over meter times 1 over meter. So the right-hand side is also in terms of amperes per meter squared. So the sanity check shows that the equation is not too bad. So given that we know what current is, J, okay, known. Okay, then we can find the charge using this continuity equation. Okay, so this will give charge. Also know, if you know what the current is, I can figure out what the charge is by charge conservation. And then if I know what the current is and what the charge is, I can find the electromagnetic field around the source. We use the vector potential approach, vector scalar potential approach. Okay, so there we say that instead of solving Maxwell's equations, we can solve two simpler couple equations. Okay, we found that the vector potential satisfies this equation. The scalar potential satisfies this equation. Rho over epsilon. Okay, this is vector potential. This is scalar potential. So the process looks quite systematic given the current source and the charge source. We just solve for A and phi, and with the knowledge of A and phi, then we can find B, which is the magnetic field. And then we can find the electric field, which is grad phi minus j omega A. Okay. So we just need to find the solutions to the top two equations that we have already done. Okay. We actually know that we can solve equation 1 above. Okay, let me just write down that solution for you that we have done before. It is equal to mu dr prime v and then j of r prime convolving with the Green's function of this system that you have already done in your take-home exam and so on. Okay, the Green's function is found to be this. Okay, but my j can be actually modeled by a point source. Okay, say if pointing in the z direction, then it will be pointing in z hat direction in this manner. Okay, and this is actually equal to z hat IL delta x, delta y, delta z, okay? So the next thing I need to do then is to plug this in and using the shifting property of delta function. Then the vector potential due to a Herzin dipole is equal to, we plug that in, I get a z hat, and then I get the mu on the outside, and then I will have IL e to the minus j beta. R prime is equal to 0 using the shifting property, okay, of the other function. R prime is set to 0. So I have this over 4 pi r. Okay, so I immediately find the vector potential A, and then using the fact that I'm in spherical coordinate, I can also write this as e to the minus j beta r over 4 pi r. Okay, where I have used the fact that the magnitude of r is just r. Any questions so far? We saw for the field, the vector potential due to a Herzin dipole quite easily now. Any questions so far? Okay, wonderful. We found the solution to Maxwell's equations for Herzin dipole now. The next thing, of course, is to find the field from this vector potential A. And actually, it turns out that those two equations are not independent of each other. Given this equation, you can always derive the second equation using Lorentz gauge, okay? So let me just milk this expression for the vector potential a bit more, okay? So I would like to find the magnetic field, and I know that mu h is curl of A, okay? And then if I know how to find curl of A, then I would know how to find A is actually given to be very simple. A is z hat mu il e to the minus j beta r over 4 pi r. Okay, let me erase this a little bit. Okay, and then I have to write down the curl in cylindrical coordinate. I use cylindrical coordinate to write down the curl. Because this function is cylindrically symmetric, it's pointing in the z direction, and r is also only a function of rho and z. Okay, so it's a lot easier to do this in cylindrical coordinate. And the curl operator, you have to do a lookup table. Okay, lookup table for this then says that the only thing that matters for this curl of A is this the phi component. Okay, let me see if I get this correct. Z. The curl of A, sorry, the curl of A, if you do a lookup table, will consist of this term. And cylindrical coordinate, it will have two terms, okay? Partial rho A of Z. Okay, so curl of A in cylindrical coordinate system is given by this. And then A phi is equal to 0 because this vector potential does not have A phi, so this term goes away. And then we have curl of A is minus phi hat partial rho AZ. The AZ is given by this, and then you can work that out. I presume that all of you know how to do vector calculus in cylindrical coordinates, okay? In spherical coordinates, you will have r hat, theta hat, and phi hat, okay? But then in cylindrical coordinate system, you have rho hat, z hat, and phi hat, okay? And if you do all these things correctly, then you will have to find dd rho correctly. dd rho can be thought of as d r d rho can be written in that way using the chain rule. So because this is only a function of R, and you know the R is rho squared plus Z squared, you can plug that in and find DD rho quite easily. And then you will find that H only has the phi hat component. And if you go to the algebra, the vector algebra, assuming that you didn't make any mistakes, let me see. I just heard some noise. I don't know what that noise is. IL over 4 pi. Okay, if you do all these derivatives correctly, I'm not going to go through the detail. I'm sure that you know how to do that. If you do this at home, okay, and then e to the minus j beta r. Okay, I'm sure that you can do this at home. I wouldn't go through the detail. And then the e is of course gotten by vector algebra again. You take the curl of A, okay, you can find the electric field by taking the curl of A divided by J omega epsilon, okay. Why is E given by that? Well, sorry, not curl of A, curl of H. Okay, the electric field is given by that. And then again, you need to learn how to write this in spherical coordinate system, because everything is better done in spherical coordinate system now. And if you do this in spherical coordinate system, you have r hat 1 over r sine theta d theta sine theta h phi, and then minus theta hat 1 over r partial r r h phi. Okay, I assume that you know how to do this at home without making any mistakes. And then what you have then is that, the electric field finally is something that looks something like this. K omega epsilon 4 pi r cubed, and then you will have r hat 2 cosine theta 1 plus j beta r plus theta hat sine theta 1 plus j beta r minus beta square r square. Okay, so you have r hat component and theta hat component. And so in spherical coordinate system, this is x, y, z. The r hat is, you probably remember your spherical coordinate system. This is phi, and this is theta hat, and r hat is pointing in this direction. Okay, you will have to go back and revise your spherical coordinate system again. Okay, and I won't teach you how to do this, but what happens is that if we were to sketch the electric field of this thing, which is kind of hard to see right now, okay, you will see that the electric field will look something like this. In the near field, it will look something like this. Okay, in the near field, beta r is much, much less than 1. So this can be 0, this can be 0, and then this can be 0. And then you only have this term and that term. And if you were to sketch out that field, it only has r and theta component, and this is how the field looks like. Okay. In the far field, of course, something is different. In the far field, then this term dominates, this term dominates, and this term dominates, and this term is negligible. Okay. So you can go to the near field case, beta r much, much less than 1 case, near field. Okay, that means that you're very close to the source, and then you could go to the far field case, beta r much, much less than 1. you have the observation point been very far away, then you can make approximation to your E, keeping only the large terms of beta R. You can show that E, okay, and the largest term of E is this term over here. If you keep only that term, you can see that E is pointing in the theta direction, and then J omega mu IL over 4 pi R, okay? Because this beta R squared, this is R cubed, then you have 1 over 4 pi R. And then you have this phase function left, okay? E to the minus J beta R. And then you have sine theta, okay? Sine theta coming from here, okay? And then you can show that H, the H field that we have derived earlier, given by this expression over here, okay, the H that we have derived in the far field would be something like phi hat, okay? Only the phi hat is left, and then if you make R very large, only this term dominates, and you only have J beta RL over 4 pi R e to the minus J beta R sine theta. Okay, any questions so far regarding the near field and the far field of the Herzin dipole? Any questions so far? Okay, so one interesting observation is this far field. If you look at the far field again, what it says is that the electric field is pointing in the theta direction. So if you go to spherical coordinate system again, I hope you go back and revise them. Okay, so if this is your R, okay, if this is your R, then, and this is your phi, this is your theta, then what it says is that in the far field, if this is a Herzin dipole pointing in the Z direction, this is a Hertz dipole. Okay, the electric field that it produces, E, is predominantly pointing in the theta direction. That's what it says. Okay, the far field is predominantly pointing in the theta direction, and then you know that phi is pointing in this direction. This is phi hat, so you draw the phi hat on that picture. That is where the magnetic field is. H is predominantly in the phi direction. So the wave is propagating in the R direction. So it propagate in the R hat direction. Okay. Again, you see that E cross H is pointing in the R direction. That's where the power should be flowing. Okay, E cross H, yes, is pointing in that direction. Okay, pointing in the R hat direction. And so our solution is correct. Okay, so this is almost like a plane wave. Because we also saw that when we studied plane wave, if you take a plane wave, you cross E with H, it points in the K vector direction. And K vector, in this case, is actually pointing in the R hat direction, because if you think of this wave as propagating outward, and if you think of this as spherical waves, you think of this as spherical waves, okay? Spherical waves propagate like this, and you can think of it as minus J beta dot R, where beta is beta R hat, R is R hat R. Okay, so this is like a plane wave. This is expression for a plane wave, but expressed in terms of the spherical coordinate system. Okay, and what is more important is that if you take E theta over H phi that you have derived here, you take E theta over H phi, you divide these two constants, they look like that of a plane wave as well. Okay, it would be J omega mu over J beta. Okay, if you look at this J omega mu divided by J beta, the other factors being the same. Okay, and this is equal to mu over epsilon, which is just equal to eta of free space, the intrinsic impedance of free space. Okay. Are there any questions so far? So the Herzin dipole is very illustrative because a lot of the physics that we like is actually embedded in the Herzin dipole. Okay. So let's look at the pointing vector that comes from this Herzin dipole and the pointing power that comes from this Herzin dipole. And we look at it in the far field because the far field physics is more interesting there. Okay. And what I'm trying to say is that in the far field, the spherical wave, this is called a spherical wave. Okay, this is called a spherical wave. It very much looks like a plane wave in the far field. These are called spherical wave, e to the j beta r over r. These are called spherical wave. Okay, because if you think of the phase front, they actually emanates like a sphere outward. And then if you were to look at the pointing vector S, the time average one is half the real part of E cross H conjugate. Okay, this is the time average pointing vector. And so if you go about and take this E and then cross with this H conjugate, the phase term would cancel. Okay, the J would also become 1. J times minus J is 1. So the expression that you get actually becomes simplified, and I would just say that it actually looks like a plane wave. And you have seen this formula before, that when you have a plane wave, that pointing vector is 1 over 2 eta times E squared. So this is plane wave like. Which means that the pointing vector, the time average one actually becomes like that of a plane wave. And we have learned that E is proportional to sine theta before. Okay, we show that E from here is proportional to sine theta. H is also proportional to sine theta. Okay, it's proportional to sine theta. And then what you have is that E square or E cross H is proportional to E cross H conjugate. Okay, and this is going to be proportional to sine square theta. Okay, sine square theta, which means that if you to plot the field pattern, it will behave like this. That is the field pattern. If you just to plot the magnitude of E, it will be like a sine theta. Okay, xz, and this is a sine theta dependence. Theta is this angle. Okay, and if you to plot E square, it will look more like this. This is E squared. This is called the radiation field pattern. This is called the radiation power pattern. Okay, and you can work this out. It's going to be proportional to sine square, and you can actually look at the power flowing out of the antenna, and then look at the total power. So you can take this time average power, take its component in the r hat direction, and integrate over a sphere, okay, a sphere at infinity, and you can show that this thing would drop off as r squared, okay, because this thing is drop off as e squared. E squared is proportional to 1 over r, and this thing would drop off as 1 over r. But ds is r squared sine theta, d theta, d phi. The r squared would cancel each other, and you will find that this thing integrates to, I wouldn't go through the detail, it's done in the lecture notes. Okay, beta RL over 4 pi squared. Okay, so the total power radiated by Herzin Dipole is given by this formula, where you have make use of a integration identity that this sine cube theta, if you integrate from 0 to pi, is 4/3. The reason why you have sine cube is because of this. There's a sine theta from here, but there's a sine squared theta from here. Okay, because when you multiply them together, you get a sine square. So the most difficult identity that you have to integrate is sine cube theta. Okay. And as I say before, all these things are done in the spherical coordinate system. Here's a nice picture of spherical coordinate system. This is the radiation field pattern. And this other one is the radiation power pattern. Okay. Radiation power pattern. Okay. And let me see. And then you can define what is called the gain function, okay, or the gain pattern. The gain pattern is defined to be actually the pointing vector in the radial direction divided by the total power radiated by the antenna divided by 4 pi r squared. So this is like the isotropic radiation pattern. So it would be SR over S average. Okay, you take the power and assuming that it's radiating isotropically in all directions, and then you find out XR. We already found out what SR should be in our previous derivation. Okay, SR, I didn't derive it, but you can actually plug this E and H and put it back in here. And you find that SR is given by certain expression. S average is a constant, and this can actually be shown to be just 3/2 sine squared theta, okay, for Hudson Dipole. And then the directivity is defined to be the maximum of this function. And for this, its maximum is 3/2, which is 1.5. So we say that the directivity of a Herzin dipole is 1.5, okay, which is essentially the maximum value that it's going to have on this plot over here, okay. So a Herzin dipole is not very directive. So how do you make the antenna more directive? You put reflector antenna. If you put a source here and then make the reflector antenna behind it, then most of the energy will be directed to the front of the antenna. You can get more directivity out of a reflector antenna. And in the lecture notes, I also modify the Herzin dipole to a dipole with the triangular current distribution. So it's quite easy to do. And then also in the literature, people do things more fancily, where you assume that the current is not a triangle, but a sinusoidal function. And then this is true if this dipole is of sufficient length that the current is not something like this anymore. This is physical because the current have to end up to be zero at the two tips of the antenna by the current continuity equation, because this is an open circuit here, okay? And this is also true for this thing, but this is at the higher frequency where you can have a sinusoidal current distribution, and voltage will look something like this. And all these are discussed in the lecture notes. And how to calculate the radiation resistance is also discussed in the lecture notes. And I wouldn't discuss them, okay? You can find the radiation resistance. These are simple circuit concepts. Any questions before I quit for the day? Any questions? No questions. Well, let me see. Okay, I will have an office hour at 3:05 this afternoon if you have any questions about the course in the take-home exam. Okay? Any questions? If not, I'll let you go. Okay, I let you go then, and see you this afternoon if you want to come to the office hour. Okay.